Good morning to one and all. My name is Sohit, roll number 4J8, and I'm from ECE section. Today, my topic is about towards an intelligent edge, wireless communication meets machine learning. Since we all know that machine learning is the upcoming future, and when this goes to another level when the wireless communication and the machine learning are interacting. Introduction. We are witnessing phenomenal growth in global data traffic, accelerated by the increasing popularity of edge devices. According to the International Data Corporation, there will be 80 billion devices connected to the internet by 2025, and global data will reach 163 zettabytes, which is 10 times the data generated in 2016. The unprecedented amount of data, together with the recent breakthroughs in artificial intelligence, inspire people to envision ubiquitous computing and ambient intelligence, which will improve our quality of life and provide a platform for scientific discoveries and engineering innovations. In particular, this vision is driving industry and academia to vehemently invest in technologies for creating an intelligent edge, which supports emerging application scenarios including smart city, e-health, e-banking, and intelligent transportation, and so on. This has led to the emergence of a new research area called edge learning, which refers to the deployment of machine learning algorithms, including supervised, unsupervised, and reinforcement learning at the network edge. The key motivation of pushing learning toward the edge is to allow the rapid access to the enormous real-time data generated by the edge devices for fast AI model training, which in turn endows the devices with human-like intelligence to respond to real-time events. So the introduction of this topic says that we are using a lot of devices, and the data is saying that till 2025 we'll be using at least 80 billion devices, and they are all connected to the internet, that is Wi-Fi or something. Uh, then a lot of data will be generated in this process. Now we are this has led to the emergence of new research called edge learning. This is nothing but deployment of machine learning algorithms into the network edge. This is what my topic is about, when the machine learning has met the uh, wireless communication. You can also say this is as the edge towards the learning edge. Now, the main guideline for this topic of learning is learning driven communication, fast intelligence acquisition, efficiently transmit learning relevant information or data, which is a main topic, main theme of our topic, to speed up and improve AM model training at edge servers. Now, learning driven multiple access. In edge learning, the involved training data are often privacy sensitive and large in quantity. Thus, uploading them from devices to an edge server for centralized model training may not only raise a privacy concern but also incur prohibitive costs in communication. This motivates an innovative edge learning framework called federated learning, which features distributed learning at edge devices and model update aggregation at an edge server. Federated learning can effectively address the aforementioned issues as only the locally computed model updates instead of raw data are uploaded to the server. Since a lot of data is being generated, and those are being uploaded from different devices, there comes a question of privacy. This motivates us for the new framework, innovative edge learning framework called federated learning. Now, this federated learning features distributed learning at edge devices and model update aggregate at an edge server, means at only one server, and this can be effectively addressed before mentioned issues like a privacy concern or uploading a huge quantity of data from different devices. So this can be clarified by the framework called federated learning. A typical federated learning algorithm alternates between two phases as shown in figure 2. One is to aggregate distributed model updates over a multi-access channel and applies their average to update the AM model at the edge server. The other is to broadcast the model under training to allow the edge devices to continuously refine their local model. Now, this is the block diagram, or you can say architecture of the learning driven multiple access. This block diagram actually says that there are local model updates where we are inserting to distributed model updates. This is the edge server, from which we are uploading it to it, and this is uploading from only one devices. This is the feature of the federated learning, which is a framework of the edge learning. As we have discussed in the architecture, one is to aggregate distributed model updates over a multi-access channel and applies their average to update the AM model at the edge server. So here we can say that there will be an AM model in the edge server where the data is being uploaded from the local model update, or you can say local data set from different devices into one edge server, and the other is to broadcast the model under training to allow the edge devices to continuously refine their local models. And the other part of the edge server will be doing refining. You can say refining the data continuously and sending them back. Broadcast model under training. In edge learning, the involved training data are often privacy sensitive. Thus, uploading them from devices to an edge prohibitive centralized model training may not only raise a privacy concern but also incur prohibitive costs in communication. This motivates an innovative edge learning framework called federated learning. Model uploading in federated learning is bandwidth. Consuming as an AI model usually comprises millions to billions of parameters. Overall, the model updates by thousands of edge devices may easily congest the air interface, making it a bottleneck for egal edge network learning. The said bottleneck is arguably artifact of the classic approach of communication computing separation. Existing multiple access technologies such as orthogonal frequency division, multiple access, so called as OFDMA, and code division multiple access CDMA are purely for rate driven communication and fail to adapt to the actual learning task. The need for enabling fast edge learning from massively distributed data calls for a new design guideline for multiple access. In this section, we prevent learning driven multiple access as solution and showcase a particular technique under this new guideline. The key innovation underpinning learning driven multiple access exploit the insight that the learning task involves computing some aggregating function of multiple data samples rather than decoding individual samples as an existing schemes. For example, in federated learning, the edge server requires the average of model updates rather than their individual values. On the other hand, the multi-access wireless channel by itself is a natural data aggregator. The simultaneously transmitted analog waves by different devices are automatically superposed at the receiver, but weighed by the channel coefficients. The above insights motivate the following design guideline that changes the traditional philosophy of overcoming interface to the new one of the harnessing interference. Now, this is the differences between the conventional communication versus the learning driven communication, which we need to adapt. So, common technology, multiple access, item. So, the target in the conventional communication is decoupling messages from users, whereas in learning driven communication is the computing function of distributed data. And the case study is OFDMA, model update by averaging the air component. Resource allocation. The target for the conventional communication is maximum sum rate or reliability, whereas in learning driven communication, fast intelligence acquisition. The case study is the reliability based retransmission and importance aware retransmission. In the signal encoding, optimal trade offs between rate and distortion or reliability, whereas in learning driven communication, this stands for latency minimization while preserving the learning accuracy. Case study: quantization, adaptive modulation, and polar code, and Grassman analog encoding. Thank you.